Hello children, welcome to Chemistry. My name is Mahantesh Shettar. Today's session will start with a fact. The fact is benzene is carcinogenic, means it can cause cancer. So with this fact, let's start today's session. Friedel Crafts reaction. Friedel and Crafts, they crafted a reaction which you call as Friedel Crafts reaction. So by the thumbnail you might have already know that it is related to the benzene ring. So this is the famous molecule benzene. Everybody knows that. Okay, how Friedel and Crafts designed this reaction, basically how the idea came to them. You know, there are some species in chemistry or chemical compounds which are short of electrons. We call them as electrophiles. We usually denote it by E+. Okay, what are electrophiles? You know, the person who don't have money, they want money. The person who don't have love, they want love. Similarly, the species which do not have enough electrons, they want electrons. So those are called as electrophiles. Now they chose one electrophile. Then there should be someone who can give electrons to them. Who are those? That is benzene. If you see the structure of benzene, what is this circle? This circle is pi electron cloud. Pi electron cloud, what is that? It is nothing but the pi electrons in the benzene. We call this is resonance hybrid structure. You can also draw the structure like this. These double bond, single bond. Okay, this double bond will keep on changing its position. Means you can also write it like this. Okay, double bond here, here, here. So overall, we will represent it by this. So we call these electrons as pi electrons, and these are delocalized pi electrons. Delocalized pi electrons means they are not stationary, they are moving from one carbon to another carbon to another, like this. So this make benzene electron rich. So now they have two things. One is benzene, which is electron rich. One is electrophile, which is electron deficient. So they just brought them together and made the reaction. But the thing here, we have two reactions in Friedel Crafts. One is alkylation, another one is acylation. What is the difference? Don't worry, the mechanism is exactly same, but only thing, the electrophile is different. What is that? Let's check it. First we will see the reaction, then we will learn the mechanism. So this is benzene ring, simple. Okay, so if you are introducing an alkyl group to this benzene, okay, you call it as Friedel Crafts alkylation, right? Alkyl group. If you are introducing acyl group, C double bond O R, this is called as acyl group. This is known as acylation. But to happen these reactions, Friedel Crafts, they need a catalyst. What is that catalyst? Anhydrous AlCl3. What do you mean by anhydrous? Which do not contain water, free from water, dry. That will be anhydrous AlCl3. Okay, we'll see what is the role of this. It is actually acting as a catalyst. Everything is simple. Okay, so here to introduce alkyl group you need alkyl halide, RX. X means halide. To introduce acyl group you need RCO double bond X, acyl halide. Okay, we'll take one example and try to write the mechanism, try to understand the mechanism. So mechanism means what? Step by step process, how it is happening. Say for example, you have an apple. how to cut apple into 6 pieces. Okay, so you will cut it into half, another half, like that you will make 6 pieces. So that is called as stepwise step mechanism. Similarly here, how the benzene is getting electrophile. So what you're doing here, you're taking the benzene. Okay, this is called as bond line notation, means we don't show hydrogens and carbons. Basically in Friedel Crafts reaction, the hydrogen is replaced by the electrophile. I'll just write E. So therefore hydrogen is substituted by electrophile. We call this type of reactions as electrophilic substitution reaction. Very simple, substitution reaction. Okay, fine. First I will select the alkylation. Similar or exactly same mechanism will be there for acylation as well. It's gonna be interesting. Now I will select any alkyl halide for doing alkylation, Rx. So I will take the methyl chloride. Methyl chloride is a common name. IUPAC name of this will be chloromethane, right? Then what Friedel and Crafts are using? Catalyst, AlCl3. Why AlCl3 is a catalyst here, we'll see that later. But what is AlCl3? It is acting as a Lewis acid. Lewis acid. Lewis acid are those species which can accept the pair of electrons. Take pair of electrons, accepting it. Whoever give it, those will be Lewis bases. Who are accepting it, those will be Lewis acids. Now see, chlorine. Now the story starts. Chlorine saw its siblings here, so it want to go and play with their siblings. So now what happens? It will not go as a Cl plus, it will go as a Cl minus, because it is more electronegative than carbon. So with this bond electrons, it will go to AlCl3. AlCl3 is happy to accept the pair of electrons because Cl is bringing 2 electrons. Okay, now it will form AlCl4 minus. AlCl4 minus. But what happened to bechara methyl? Methyl is short of electron. Short of electron means it is positively charged. What do you call such species? Carbocations. Carbocations. Right? So this is primary carbocation. Now methyl is short of electron. It will do this. Okay. So then it want to get stable, right? Who will help our methyl carbocation? Benzene. So that will be your second step. First step, what you did, you generated the electrophile. You can write it as generation of electrophile. Second step, what you can write? Attack of electrophile on benzene ring. So benzene you take. What is the electrophile here? Methyl carbocation. Write it. Benzene is rich with electrons. Methyl is short of electrons. Benzene asks methyl, would you like to join me? It is more than happy to join benzene because it is getting stable, right? So you show it like this. So benzene, always electron arrow mark should be from electron rich to electron poor. Okay, now so what is happening? This bond, the carbon-carbon bond will form, right? So I will write here. I'll just show here hydrogen is already there. Remember, all hydrogens are there. Methyl group introduced. Okay. What about this carbon? It is now, okay, these bonds, nothing will happen. Now this carbon is short of one bond, means it will have the positive charge. Basically, the positive charge is shifted from methyl group to this carbon. You can see. Okay. Now methyl is asking benzene, have you done any mistake by taking me? by accepting me, because you are getting the positive charge, you are getting unstable. Benzene told, don't worry, I have more than one carbon. I can stabilize this positive charge. I can distribute this positive charge. I can still be stable. Okay, so what we write here, we show this kind of arrow mark. Okay, what do you call this as? Canonical structures or resonance structures. So this bond will come here, the positive charge will shift here. So write that, do it step by step, don't miss any step here. H and CH3 as such, positive charge here. Again, this bond will come here, so the positive charge shift here. I'll just write it like this because I have no space to write. Okay, a new bond form here. Here, this H and CH3, nothing will happen. This is getting the positive charge. Okay, now if you observe positive charge here, here and here. So overall, for these kind of structures, we write a resonance hybrid. What do we write? A resonance hybrid, like this. So you keep H and CH3 same, but this positive charge is distributed here. So we show it here. We don't show it here because this carbon do not have any positive charge. What we call this? We call this as sigma complex. Sigma complex. Okay. Now the sigma complex is stable, but it cannot stay like that forever. Now it's the time for the sigma complex to do. Sigma complex is thinking, shall I lose methyl or shall I lose proton? Okay, obvious choice, but it already gave its words to methyl. I will not leave you, but it can leave proton because it already has many hydrogens here. So then who will help? How the proton will go? That will be the next step. So next step I'll write here. Okay. Third step, write the sigma complex as such, with hydrogen, with methyl and positive charge. Now where is the base? Remember, base is the species which can accept the proton. Our AlCl4 generated in the first step, that itself is our base. Okay, Cl minus whatever went with AlCl3 now wants to join with proton. You know, understanding the story means Cl minus will take the proton, it will form HCl. AlCl4 minus, Cl minus gone, AlCl3 left. Then once the proton is absorbed, this bond will come here and the benzene will become stable again. The benzene ring will become stable again with the CH3. You know what happened? Initially started with benzene with hydrogen here. That hydrogen is substituted by methyl group, right? So we call this as commonly toluene. Toluene. Okay. Similarly, instead of methyl group, you can also put ethyl group. You will call it as ethyl benzene. This you can also call as methyl benzene, right? Okay. What about this is alkylation. What about the acylation? Exactly same mechanism. Only thing, instead of methyl or alkyl electrophile, you are producing acyl electrophile. You call this as acyl group from acyl halides. This is acyl halide. Okay, so you produce this will come and stick to benzene ring. Okay, shall we write that? Can you try it yourself? I will also write it here. So just erase this step. Okay, we'll write here acylation. Fine. The first step is what? Yeah, correct. Generation of electrophile. Let's generate the electrophile. I will take the acetyl chloride. Okay, this is one of the acyl chloride, that is acetyl Chloride is the common name. Its IUPAC name will be ethanoyl chloride. Ethanoyl chloride. Oil halide will be the secondary suffix. Remember. Now again the same catalyst AlCl3. The same thing happens with chlorine. It goes with AlCl3. So you will get AlCl4 minus. What happened to CH3CO? It will form the carbocation again. So it's now the turn for this acetyl carbocation to do. Next, this I will keep same, just change. Instead of methyl group, second step what? The electron rich benzene will attack the electron deficient electrophile, that is our acetyl carbocation. So here C double bond O CH3 plus. Remember, it is going to attach the carbonyl carbon. This carbon is called as carbonyl carbon. Okay, just keep on replacing that. C double bond O CH3, C double bond O CH3. Everything same. It is also stabilized, right? Okay, resonance structure, resonance hybrid. This sigma complex formed. Now again it's the turn for sigma complex to do. Okay, again who will help it? Same fellow, AlCl3 will help to take out the proton. So I'll just take it out and write it here, sigma complex plus HCOCH3. This H will be taken by AlCl4 minus. Okay, this will be third step. Okay, what is happening? H go with Cl, you will get HCl plus. What happens to AlCl3 remains as such because it's a catalyst. Catalyst you know already, right? It chemical composition do not change, but it accelerates the reaction. Rate of the reaction it will change. Okay, now what happened? This bond will come here. You will get acylated benzene, you can say. What is this name? Particular, this compound is acetophenone. What it is called? Acetophenone. So they may ask you, how do you convert benzene into acetophenone? That will be Friedel Crafts acylation. How do you convert benzene into toluene? Friedel Crafts alkylation. Understand? So this is the whole story of Friedel Crafts reaction. Hope you understood. If you have any questions, please put in the comment section. Thank you so much for your time. If you like the video, please share, subscribe and like. Thank you.